name's Carl Schmidt. I'm a researcher at a laboratory called LATMOS in Paris, France, and I study planetary atmospheres there. So Mercury's atmosphere is very similar to the moon, and that's maybe a better place to start talking about how an atmosphere of a very thin, ballistic atmosphere on one of these bodies works. There's a couple different ways to form an atmosphere on a body like Mercury or the moon. And we don't really know the relative importance of these different methods for creating the atmosphere. People have argued about them for a long time, and they're very hard to disentangle. One way is by ultraviolet photons from the sun energizing particles on the surface and them being liberated from the surface by photons from the sun with a couple eV of energy. In Mercury's case, the surface gets so hot, up to 700 degrees Kelvin, that you can actually evaporate the rock directly. And we're trying to understand which elements can be evaporated versus which elements require a different form of energy in order to liberate them into the atmosphere. The ions from the solar wind will directly impact Mercury's surface. On the Earth, they would collide with the atmosphere and cause things like aurora, but there's no atmosphere that is collisionally thick in order to stop the plasma on a body like Mercury or the moon. So those ions impact directly, and they sort of garden the surface in order to liberate material that way. And there's a constant spray of meteors, particularly near comet tails, that is always persisting in the ecliptic plane of the solar system. Those meteors, when they collide with the surface, they vaporize and cause some gas material, and some of that gas can actually form a thin atmosphere around a body like Mercury or the moon. So these particles, which are liberated from the surface and lofted, are released with different energies for each of these different processes that create an atmosphere. Those energies, if they're substantial enough, will be affected by solar radiation pressure. Radiation pressure is very strong on Mercury because Mercury is close to the sun. And it's due to photon momentum. So particles of sunlight, photons, have a momentum which corresponds to their wavelength, more momentum for shorter wavelengths. That momentum, when sunlight scatters off of an atom, is transferred to the atom, and it gives it a push. Momentum per unit time is a force. That force is radiation pressure, which pushes things anti-sunward. So all of Mercury's atmosphere, because it's so close to the sun, is being pushed away from the sun. And particles which exist in the atmosphere for a long time feel that push over a longer period of time, and it distorts the atmosphere into a tail. So that lunar sodium tail is reflecting this distortion, and that sodium tail is much more pronounced at Mercury because the sunlight is much stronger there. So we can push things into a tail by sunlight, but if we ionize them, because the sun has all sorts of ultraviolet output which can ionize atoms in the atmosphere, those ions will get trapped in the magnetic field, and that gets swept anti-sunward into a tail also. So we have an ion tail and a neutron, and a neutral tail rather. You don't need a large telescope to study these effects. With the lunar sodium tail, you can use a coronagraph to block out the reflected light off of the moon and image the atmosphere on that. And you can use a coronagraph to study the escaping atmosphere of Mercury in much the same way. So there's a little filter here which is blocking out the bright light from Mercury so that we can image that sodium tail that's being pushed by sunlight escaping it. Because Mercury is so close to the sun, we always have to look at twilight in order to see this, just after sunset or just before sunrise. So this sort of distorted pattern on the bottom of this image on the left here is actually trees. We're tracking something rising or setting right near the horizon, and during, in this case, a 6-minute exposure, those trees will get smeared through the field of view. Some observatories have difficulty observing that low to the horizon because there's actually trees in the way. These background stars here, just to the right of Mercury, that's the Pleiades. In Japanese they call it Subaru. And those stars have a very well-known brightness at specific wavelengths, and it's useful for calibration. So in order to figure out exactly how much sodium is being lost from Mercury's atmosphere, we subtract off all the background from Earth's atmosphere and calibrate using those standard stars, and are left with what is the brightness of the Mercury sodium tail. That brightness changes as a function of time, and it reflects a change in Mercury's atmospheric loss rate, but it also is due to natural effects independent of Mercury's atmospheric loss. And it's that which we can study with small telescopes, like this 10-centimeter aperture. So the orbit of Mercury isn't exactly circular. It's one of the more eccentric orbits of bodies in our solar system. That eccentricity will give it some Doppler shift, where sometimes Mercury is moving towards the sun and sometimes Mercury is moving away from the sun. That changes the amount of sunlight that is seen by different elements in the atmosphere because of Doppler shifting. So the sun has trace amounts of sodium, calcium, potassium, all of these things in its atmosphere. Those cause absorption wells, so they block sunlight at certain frequencies from getting out of the sun's atmosphere. And those are very narrow features, so when we Doppler shift relative to those, it changes the incident sunlight by quite a bit. So this Doppler shifting at Mercury will change the planet's relative velocity to the sun by about 10 kilometers per second. And we get similar effects at Jupiter and more pronounced for comets. The amount of sunlight which is available to be scattered off of those atoms changes by a factor of 20. So independent of how much we're losing in atmosphere, we can observe a change in brightness by a factor of 20 just by how much sunlight is being scattered. Because those scatterings cause radiation pressure, that determines how far the sodium tail will extend, how far those atoms will travel before they're photoionized over a couple of hours, and it will determine the overall brightness that we can observe with these telescopes. So as Mercury is orbiting, the sort of 1/r squared distance from the sun effect changes the overall DC background of sunlight, and then these two absorptions from sodium in the sun's atmosphere cause these very deep wells, and we're Doppler shifting Mercury relative to those wells during every orbit. That changes the brightness of the atmosphere substantially in a way that's independent from actual changes in the atmosphere. And so it gives a complicated function that needs to be corrected for in order to understand physical things about it. You can apply correction factors that are really only approximate because the individual atoms in the atmosphere have their own Doppler shift. And in order to factor those in and account for optical depth, self-absorption of the atmosphere, the best approach is really to use what we call a Monte Carlo model, where you roll the dice in a Monte Carlo sense and use a random number generator from the outcome in order to predict one thing or another by running it through a series of physical processes and equations. So just like when Mercury is moving away from the sun, we have a Doppler shift where we see a bright feature. Atoms moving down the tail will have positive and negative feedback. The faster it moves away from the planet, the more sunlight it interacts with, because it's Doppler shifting out of that solar well. And the more sunlight it interacts with, the more it accelerates. And it's a runaway process where it accelerates the whole atmosphere away from the planet very, very quickly. When Mercury is moving towards the sun, there's negative feedback instead of positive feedback. And so the atmosphere Doppler shifts into an absorption well. It interacts with a lot less sunlight. And we don't really see any escaping atmosphere because it's not visible. And there is no distant tail behind it. But it can still get far enough from the planet that it will Doppler shift all the way into the solar well and then back out the other side. Once it comes out the other side, it starts getting bright again. The feedback becomes positive, and you can get an isolated blob of a bright atmosphere that's very, very far from planet Mercury, just because it's gone through this process where it Doppler shifted into an area where there was no sunlight scattering it, and then back out where there's a runaway process where there's positive feedback and a lot of sunlight. It gives you a blob of atmosphere just sort of floating out in space that otherwise you would have no idea where that emission came from. To try and figure out what Mercury's atmosphere is sustained by, what process is creating it, we can use Monte Carlo models with different velocity distributions and compare that to the overall distribution of the atmosphere that we see escaping planet Mercury, the width of the tail and the fraction of the tail that we think is, atmospheric loss relative to how much atmospheric source of the atmosphere is coming from the surface. And so if we sort through those processes of meteors, ions, photons, and just the hot surface evaporating, each of those have their own velocity distributions associated with them leaving the surface, and they all would produce very different observable tails. So on observations here in the first panel A, and the different processes would give you a different shaped atmosphere correspond to the other panels here. It works pretty well in terms of matching to micrometeorites sustaining the atmosphere or to ultraviolet photons. But it doesn't work for what was predicted to cause an energetic escaping atmosphere on planet Mercury. That is, if you take all of the ions coming from the solar wind that are hitting Mercury's surface and liberating material, it's still not enough to explain the brightness that we've observed. The observable brightness that you'd see from that is at least a factor of 10 too low to match the data. So we're learning new things just by only isolating an escaping portion of the atmosphere, and you can learn them with small telescopes.